Good afternoon, everybody. And I would like to start with a thank you to everybody in the room. Thank you for coming over for our inaugural seminar event. And also thank you to everybody on the phone. So this is the Power of Applied Chemistry Seminar Series. And this is a seminar series that Levi and I talked about last year. And we said, how great would it be if between Chemours and UD we can get together, we can bring in big name speakers that can talk about cutting edge science, and then we get our scientific communities together where we know further collaborations will grow and prosper. So we're very excited to have Dr. Schrock here as our inaugural event, and with that I'm going to turn it over to Levi to introduce Dr. Schrock.
So thanks, Tim. Working with Tim has illustrated how chemists and chemical engineers, or scientists and engineers, can work very well together. This is actually that brainchild or idea that we had many years ago, or last year, that took about a year to bring to fruition. Really proud to introduce Richard Schrock, today's speaker. I'll tell you a little bit about him. Of course, those of you who are inorganic chemists probably know more about him than I do. In fact, I know that some of his former students and postdocs are in the audience, and we had a wonderful lunch just talking about his relationship with some of you. He is a graduate of University of California at Riverside, got his Bachelor of Arts degree in 1967. He got a PhD at Harvard in 1971 for the graduate students in the audience, 4 years. Probably makes you a little nervous, but if you do that, you get a Nobel Prize, right? He spent a year as an NSF postdoctoral fellow at Cambridge, and then 3 years in our community here in Delaware at the Central Research and Development Department for DuPont. He was then swept away to be on the faculty at MIT, and so for our faculty, he started out in 1975, and by 1980, he was a full professor, so 5 years. You start out as an assistant professor and get to full professor in 5 years, you get a Nobel Prize. He has since retired from MIT, and he is now the George Helmkamp Founders Chair of Chemistry at UC Riverside. You know, again, that's his alma mater. He also has appointments at other institutions. And just to give you a sense, of course, he is a Nobel laureate. I'll tell you a little bit more about that in a second, but he's also recipient of the Alfred P. Sloan Fellow, Camille and Henry Dreyfus Teaching Scholar Award. He has a number of awards from ACS, the American Chemical Society. He's an Alexander von Humboldt Award winner. Many lectures, endowed and named lectures across the world, in fact. And as I mentioned earlier, he's a Nobel laureate in chemistry, sharing the 2005 Nobel Prize in Chemistry with Yves Chauvin and Bob Grubbs. He was elected to the American Academy of Arts and Sciences and is elected member of the National Academy of Sciences. He's published more than 600 papers. I see 615. I didn't actually do the count myself. During lunch, we learned that he's published 80 with one collaborator. So how many of you have more than 80 papers? Wow. So he's published 80 papers with one collaborator, a high bar to reach. His contributions to Metathesis have been extraordinary, allowing us to more efficiently synthesize a variety of organic molecules. A consequence of that, for those of us who are on the applied side, is that these chemicals can now be produced in ways that are much more energy efficient, cleaner, and environmentally friendly. I met Dick as part of the Center for Enabling New Technologies Through Catalysis, or CENSI. He was an inspiring contributor to the work there, and his engagement in the center was not only for the work that he does, sort of the basic chemistry work, but he seemed to think about the impact and the commercial possibilities for the work that we were doing. And that is one reason why we thought he would be the most appropriate speaker for this inaugural lecture. His work has impacted the way a variety of chemicals have been made, from herbicides to fuel additives to advanced polymers. And of course, metathesis today is being used to hunt for all kinds of new pharmaceuticals. And so, without further ado, join me in welcoming Professor Richard Schrock.
Thank you, my man. Well, it's been a long time since I've been here. People ask me if I've ever been to the University of Delaware, and I think when I was at DuPont, there were some programs that involved a regional meeting of organometallic chemists or something like that. And I did come occasionally, but I didn't have a close relationship. My wife has a closer relationship. She got a master's degree from the University of Delaware. She's a fighting blue hen, as she reminds me. It's a pleasure to be here. I'm on my way back from California, where I spend 3 months of the year, back to Winchester, Massachusetts, where Nancy, my wife, and I live. Now, this is supposed to be on applied chemistry. The way I see it, everything is chemistry. So whether it's applied or not is really a question of judgment. And I am more interested in fundamental chemistry. But I also learned when I was a graduate student and probably at DuPont what could be of value in chemistry, more than just making something you can sell and convincing somebody to buy it. And that is to have a permanent impact on how chemistry really is done. And that's actually what the Nobel Committee thinks about when they consider people for a Nobel Prize. They say, well, how does this person influence other fields? Not, are they the smartest person? Not, have they written 1,400 papers? It's what have they actually influenced in chemistry? Other fields. I'm going to talk about I'm going to take you back to the beginning. So this is my group now at Riverside. So this fellow, Sumang, has just left. So I have 2 postdocs here. Most of the work is going to be by this fellow and this one here. And it's all about what's happened in the last year, at least when I get to the point where I start talking about results. This first slide is what happened in 1974 at DuPont. So I had the fortunate opportunity to be at DuPont at a time when it was a thriving organometallic research community. It was called the Experimental Station, and Jeffrey Wilkinson was a consultant. And I talked with Jeffrey Wilkinson and was inspired to do a few reactions involving tantalum, which is right next door to tungsten in the periodic table that I know you all know by heart. And there might be some analogies. And what happened is that I was attempting to make penta-neopentyl tantalum. So I guess this is not going to work. No. Okay, so in the lower left, penta-neopentyl. So neopentyl is just T-butyl methyl, and then 5 of those. So I worked up from pentamethyl to pentabenzyl to penta-neopentyl. Penta-neopentyl doesn't exist. It eliminates neopentane. Shown at the top there, you make it as an intermediate in this reaction, as shown by Zuling Xu. And interestingly, the deuterium isotope effect that he found for that was rather high. It's an interesting thing to think about now in view of what I'm going to talk about. But anyway, 1974, that was my big discovery. There's no compound like it. There's no tribenzylbenzylidine, or no trimethylmethylidine. These are all very low electron count, 10 electron species. And number 2, it was a new type of compound, the highest possible oxidation state of tantalum, if you count the alkylidine, the CH-T-butyl, as a 2- ligand, analogous to oxo, for example, or NR, imido group. And number 3, it was so fantastically thermally stable. Now, these are all air-sensitive, moisture-sensitive reactive compounds. And that was a very, very interesting phenomenon to find that this compound melts. And if you put a good vacuum on it, it will actually distill and crystallize. And I think Klaus Leopold knows how fantastic experience like that is, an experience like that is. So, new compound. The mechanism, I call it alpha hydrogen activation or abstraction. The alpha hydrogen gets pushed towards the metal, and that CH bond gets activated towards being removed. I proposed that it was actually as a proton. That's still debatable, as we'll see today. But in any case, you do make neopentane and make this fantastic new compound. And in 1971, 2, 3, 4, when I was at DuPont, 2, 3, 4, 5 actually, there was a new reaction out there discovered by, initially debatable by Herb Eleuterio at DuPont, who is now over 90 years old, I think, I was told. And it's called the Olefin metathesis reaction, or that's the name that it took on over the years. And it's close to 60 years old, therefore. And what it does is Malcolm Chisholm, another organometallic type, like me and Klaus, called it the chop-chop reaction. So you chop up one olefin of one type on the left, say an R prime olefin, cis or trans, and you equilibrate it with the other two possible cis or trans olefins. So turn one olefin into 6 different olefins, which is not very useful, but several people, like Bob Grubbs and others, realized that this was a totally new organic reaction, and nobody knew the way it worked. And I had just made a compound that contained a metal-carbon double bond, which Yves Chauvin, 1971, proposed was the catalyst, or had proposed at the time I did the tantalum work, was 74. So the metal-carbon double bond reacts with a carbon-carbon double bond, and you make a ring. That's reversible. You can do it either way, and if you sit down and think about it for not very long, you can see how you can scramble the ends of olefins in that way. But nobody knew what catalysts are formed or what they are. They certainly aren't of tantalum. They are of molybdenum, tungsten, and or rhenium. So over the next N years after 1975, when I went from DuPont to MIT, I was fortunate enough to get a job there, and I developed a way of making those metal-carbon double bonds on molybdenum or tungsten, which are probably, since you have to add those to do this reaction, you're going to make metal-carbon double bonds of molybdenum or tungsten, but we didn't know what they were. So it took a while to figure out, and here you see some time periods and the types of compounds that actually do the reaction, where the CHR is usually one of those on everything. There's a neopentyliidine there, it's a CHR, and so on. And 4 ligands total, and an electron count that we talk about is at the metal, 14 electrons used for bonding between the metal and the ligands. So they're very electron deficient. They're all 4-coordinate. If you add some other ligand, like a phosphine or something that binds with the metal strongly, then you get a 5-coordinate species. That's inactive. You can add even another ligand and make a 6-coordinate species. That's an 18-electron compound. That's inactive. It has to be 14 electrons, as far as we know. Many of the ligands are big ones. Why are they big ones? Like this one in the lower right is a terphenoxide. It's a phenoxide, but it has a couple of rings in the 2-6 positions, very bulky. And the reason is that if you work in solution like I work, you've got to stop intermolecular reactions. That's one of the ways that these alkylidines decompose. And so sterically, you've got to prevent these 2 porcupines from getting together. So they have to be bulky ligands, but yet they're very electron deficient catalysts, metal centers, and the ligands, or the substrates, are olefins, which are relatively small and can get in there and make the ring, which is a 5-coordinate Metallacyclopentane. There are 2 types we learned over the years. One of them on the left is what we call a TBP, a trigonal bipyramid. So you have an imido group up at the top, trans to a terphen oxide of a different type, 180 degrees apart. Then in the central equatorial plane, you have the Metallacyclopentane ring. This one has no substituents on it. It's one of the easiest ones to make. And a dimethylpyrrolide in the back. That's the catalytically active form. That will lose an olefin and make an alkylidine. However, TBPs are often easily converted to SPs, or square pyramids. That's another energy minimum in the 5-coordinate regime, not just of this chemistry, but throughout chemistry in general, organometallic or not. And on the right, you see one that's a square pyramid, crystallographically characterized, that was made by adding this norbornadiene with 2 trifluoromethyl groups on it to a neopentyledine, and it stopped. It's inactive. You can't make a new you can't make a new alkylidine, rearrange that ring, unless you go to a TBP. But if that's slow, as it is in this case, with T-butoxides on the metal, then it stops there. So this is a situation where the TBP, as it turns out, does all the work and is the magic intermediate, but it has to have a certain structure. It has to be, as I said, a TBP. And some recent calculations by Christophe Copperet, who I've collaborated with, and Odile Eisenstein, explained what is happening in metathesis. The metal carbon-carbon-carbon ring that is in the equatorial plane has also an empty orbital in between the carbons in the 2 alpha positions. It's a dxy orbital, z-axis is up and down, and it's empty. And it's really that orbital that provides the grease for the reaction. If you just do a little arrow pushing, you're going to make an alkylidine, CH2, and an ethylene, which I drew as a dotted line because nobody's ever detected this intermediate alkylidine ethylene. The olefin just comes out, boom. The intermediate on the left is a 14-electron species, and you have to go through then what you might call a 16-electron count, so maybe that's a little bit higher energy, and that's why you can't see it. And the square pyramid, the one that TBPs are in equilibrium with, that same orbital, the dxy, is still there. It's parallel to the, more or less, the plane that the 4 basal ligands sit in. There were many problems beyond just figuring out what compounds did what, and one of them was what's called the cis problem. So instead of taking one olefin and making a mixture of cis and trans olefins of 3 different types, you would like to take cis olefins and make cis olefins. Well, cis olefins are a slightly higher energy species compared to trans, so you really there has to be a kinetically controlled reaction. If it's thermodynamic, it usually goes to the trans. And we did that by showing that you could make catalysts that are shown on the left that have 4 different ligands, one of them being the alkylidine. And if the OR group, or OR prime, is large, and it ends up in the axial position, as shown in the middle, where the blue olefin comes in and you make that metallocycle, that's the only one that can form, with the R groups pointed up, away from that big ligand. And so the new alkylidine that forms, and the product is cis, Z, and the new alkylidine is what you started with, shown on the left, where R1 is on the left and R2 on the right, so it goes again. In the process, the configuration at the metal inverts, and that has some major consequences, especially in polymer chemistry, that I'm not going to talk about today. I'm going to talk about really a mechanism, but I wanted to tell you, since I visited Chemours right over there, and they were interested in electron withdrawing groups on olefins, fluorides in particulars, and people have often speculated, well, what about electron withdrawing olefins? And as an organometallic chemist, and I think Klaus would agree, if you put electron withdrawing groups on an olefin is basically a base, and then it does back bonding from the metal. But it just is not basic enough. At least that would be the supposition. I've been in collaboration with Emir Hoveda for since 1996, so over 20 years now, 25 years. And of course, organic chemists don't care about theoretically how something bonds to a metal. They just try it out. And we were interested also in alkylates that did not contain carbon and hydrogen only, but things with other groups on them. I'm not really going to talk about that. Not only in general elsewhere, but right on the alkylate carbon. And halide was one of them, because you make a CHCl compound. And the organic chemists Hoveda were interested in that question too, and discovered that they could do a cross metathesis, so shown at the top. That G is some group of interest, and it's a terminal olefin, and you can chop that one and chop the dichloroethylene and make two products, one of which is vinyl chloride, which you don't care about, common chemical, and then the chloro-substituted olefin with G that you do care about, a big biologically interesting group, stereoselectively cis, basically 100%. So that's shown here, 98%, first one on the left. That's what organic chemists do. They do all the variations. I do all the organometallic variations. Usually 98% Z. And that was a huge surprise. We published this in 2016, not so long ago. I thought I had two of those, but I've only got one of those, which gives you some idea, and I won't talk much about it, about how interesting it is to apply this totally new reaction to organic chemistry, to polymer chemistry, and we'll even see at the end of this talk some basic olefin chemistry in industry today, and that's really applied chemistry. So what I did when I went to UCR in 2018 is to ask myself, what can I do? I'm not going to, cure cancer, and so on. What do I want to do? And the answer to both of those is what I've always done, finish the job that I started in 1974. And what is there to finish? Well, classical catalysts are made from metal oxides on silica. And then you add olefins, and you get the types of compounds that I talked about. Oxoalkylates bound to the surface through an O-silicon bond. Well, at least one. We think it's just one. So how does that happen? Well, there's a whole list of possibilities. One is the one you talked at you see at the top. You ask somebody, how does this happen? They'll say, oh, the olefin just rearranges. An H moves from one carbon to another carbon, one way or the other way. Move. What do you mean move? I mean, it doesn't do that in general. How does that happen? Well, you add an H from somewhere. Could be from external, could be from an internal source, call it CH activation within a ligand. And myself in 1994 and Pete Wolzanski wrote a beautiful paper in 2005, both involving niobium and tantalum, that showed that you could rearrange an olefin to an alkylidine this way. So that's one possibility. Another possibility was what you see in the middle, 1979, a very talented student, one of my first students at MIT, Steve McLean, who came to work at DuPont and spent most of his career here, encountered in the process of examining basic reactions of tantalum alkylidines, which is some of the first things we did in the late 70s, that you could add an olefin to a tantalum alkylidine and make a metallocyclobutane that would rearrange to a new olefin, be displaced by ethylene, let's say, and then you could make metallocyclopentanes, tantallacyclopentanes, shown here second from the left, metal with 4 CH2 groups or substituents on those groups at some point. But that would rearrange to the product, not through the way that we would generally did propose, but the ring contracts from a 5-membered ring to a 4-membered ring. And then that 4-membered ring, methyl metallacyclopentane, methyl substituted metallacyclopentane, itself rearranges, and propylene comes off, and ethylene adds, and you make the product. The reaction mechanism, the so-called ring contraction mechanism, this was a theory. I'll show you what I said in the paper, because we didn't see any metathesis products. That would be, the last steps would be a metathesis, breaking up a metallocycle. It continued to rearrange. But I remember when he came up with that theory, he phoned me on a Sunday night. Back then, students worked on Sunday night. And he said, you know, we did the labeling, deuterium labeling. I isolated a compound. We ran an NMR and so on. And it's not consistent with the mechanism we proposed. And I said, well, wow, why don't they try and figure it out? So the next day, when I talked to him, he had figured it out, and it was ring contraction. So that's another possibility that has been ignored for the last 43 years by everybody, including myself. Another one is a possibility that an olefin does get CH activated, and you make a pi allyl hydride. Then the H goes to the central carbon, Metallacyclopentane. That's proposed by Christophe Copperet and Mashima in the last couple of years. So when I went to Riverside, we had made a couple of compounds. One on the left by Smiranda Marinescu in 2010 is a styrene complex drawn as a metallocyclopropane. This is the ambiguity. Is it an olefin complex, or is it a metallocyclopropane? I happen to draw it as a metallocyclopropane. And on the right, we have what you would get by moving the H from the carbon that has the phenyl group on it to the CH2. You'd get a methyl phenyl compound, which Jordan Taylor, one of my first postdocs at Riverside, showed you could make. And they have 2 isomers, because the alkylidine lies in the plane of the screen, so the one with the phenyl up and the one with the phenyl down. And could we find a way to interconvert those? And that's what Sumeng Liu, one of my first postdocs about 3 years ago, discovered. He found that an acid, external acid, dimethylaniline, shown right in the middle, with what we call BARF as the anion, because it's a relatively non-coordinating fluorinated anionic borate, which has a pKa in water of about 5.1. Of course, I don't do any reactions in water, but that gives you an idea. It's not a very strong acid. It's like acetic acid. We'll protonate the olefin, the styrene on the left, selectively at the CH2, and then remove the carbon in the presumed alkyl that you get from the carbon containing the phenyl ring to give that alkylidine. You could establish that equilibrium. It was slow. It took days, but these compounds were stable. They didn't give a lot of decomposition products, just established that equilibrium. So it proved that an alkylidine and an olefin were very similar in how they bound to the metal, and the energies of those 2 compounds, free energies, are roughly the same. Surprisingly, nobody had ever shown that before. So that was one of the things. Also, this is for molybdenum or tungsten. Tungsten behaves exactly the same way, which is kind of strange, because 3rd row metal, 2nd row, you might expect some differences, but there weren't any in that case. The intermediate is this cationic molybdenum compound with this non-coordinating or weakly coordinating anion, which is molybdenum 6, as we say, highest possible oxidation state. And it has both alpha, it has 1 alpha proton on the carbon bound to the metal, and then 3 beta protons. If you remove the alpha one, you go to the alkylidine. If you remove the beta one, you go to the olefin. And you establish, therefore, that equilibrium with a catalytic amount of acid. These are very rare compounds. You don't find a lot of these lying around, these alkyl cations. Very unusual. So we published that, and well, there are the conclusions. These are first interconversions of an alkylidine and an olefin. But it's likely not to be a general reaction because the details are so specific. Got to have an acid, non-coordinating anion. If the anion is coordinating, like chloride, it'll just bind to the metal, and so on and so on. And it's very specific for styrenes. And we've been studying it since then. We haven't published the paper yet, but basically it doesn't work for a lot of other olefins. One, because it won't protonate the olefin unless it's a CH2. And number two, olefins that have longer chains will isomerize up and down that chain and not be protonated once you make an internal olefin. So, and there's no evidence for forming any terminal alkylidines, which is another possibility. So, number two in the list is the ring contraction. So, I thought, you know, we often think that Metallacyclopentanes are, well, I thought it, many other people have thought it. Papers have been published where in the title it says Metallacycloalkanes are dead ends in metathesis. Why? Because nobody had ever taken a Metallacyclopentane. First of all, they are formed, especially with ethylene, unsubstituted Metallacyclopentanes. Nobody had ever taken one of those and turned it into an alkylidine. In 1979, Steve McLean and I published this paper where we dimerized olefins via Metallacyclopentanes. For propylene, the ones and other R groups, you can go, R groups shown there in the middle, can be either H all the way up to neopentyl. And you make a Metallacyclopentane, you can observe the top one, the beta-beta prime disubstituted Metallacyclopentane, trans R groups. You can't observe the bottom one. But as R increases in size from methyl out to neopentyl, the dimer you get is 98% the top one, the tail-to-tail dimer. That comes from the beta-beta prime disubstituted metallocycle. And for neopentyl, the head-to-tail dimer, the bottom one, that has to come from the unobservable alpha-beta prime substituted Metallacyclopentane. Now this is true in a lot of chemistry. What you see is not what the most important species might be, the catalyst in a reaction in my case. But I propose then, as you see, the metal C4 to metal C3 ring contraction, which is what this is, it contracts twice, or it contracts and then rearranges, contracts and rearranges, is a straightforward and reasonable way, I don't know how true that is today, or then even, of forming an alkylidine ligand from olefins. I'm thinking about molybdenum and tungsten now. Assuming that some complexes, MOC3, metallocyclopentanes, and metallocyclobutanes, which form in this manner, will cleave to give metathesis-type products instead of rearranging. So I asked Maxime Bougelal, who left my group about 2 years ago, let's make some of these metallocyclopentanes. There aren't very many. There are about half a dozen crystallographically characterized because they're not very interesting, obviously. You can't make an alkylidine from a metallocyclopentane. Let's just check that out. So he made the compound shown at the top. The R group, AR group, is diisopropylphenyl and triphenyl siloxide, so that kind of mimics the surface to some degree, if that's important. Dichloride, and treat that with 2 equivalents of an alkylating agent, ethyl grignard, ethyl magnesium bromide. And you make, under ethylene, the metallocyclopentane in good yield. Now, how does that happen? 2 ethyl groups at some point are on the metal. One ethyl group takes the beta hydrogen from the other, makes an ethylene complex and ethane, and then ethylene that's above the solution adds to that ethylene complex, makes the metallocyclopentane. And this is a fluxional compound, so if you look at the NMR spectrum, you should have on that ring 2 protons up in the alpha position, 2 protons due, beta protons up, 2 down, you should have 4 signals. But you only have 1, this lump at about 3. And the reason is that this metallocyclopentane, like many 5-coordinate compounds, is fluxional, as I pointed out, going through, converting to a TBP and back again. And whenever you see, a broad signal, you cool it down and you see if that's a fluxional process. And so if you cool it down at the bottom, you see what you get. These proton chemical shifts are very similar, so you get a complicated spectrum. At the top, you get two signals, one for the alpha protons, both up and down, and one for the beta protons, up and down, because the ring flips over. Boom, 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 like that. So you get 4 to 4 at 359 K. The intermediate has to be, in order to do that, this TBP. There's another possibility, but this is probably the one which has a plane of symmetry there that equilibrates the CH2s in the alpha position and the CH2s in the beta position one way or the other. The crystal structure of that square, well, it turns out to be the square pyramid. That's the lowest energy compound. Nothing unusual about it. The 5-membered metallocyclic ring is distorted this way and that way, so that's a disorder in the solid state structure. Very common for these rings to do that. Only unsubstituted metallocyclopentanes had been observed at this point. And as I said, only a few had been isolated. So I said, well, let's look, see what happens with C13 ethylene. We know ethylene goes in and out, probably. That's the way it's formed. So what's the rate of that reaction? I always think about mechanisms, kinetics. And so he got some C13 ethylene, and he started to incorporate it into the ring. So presumably the ring breaks up, you form the ethylene complex, C13 ethylene comes in and happens again. Ultimately, you get the fully labeled, or a mixture actually of the doubly labeled and fully labeled metallocyclopentane. And after 10 minutes, you see at the top then very easily, because it's C13 labeled, 100%. That one's 50%, this one's 100%. On the left, around 70, you see a doublet for the alpha carbons. And at about 35, you see a doublet for the beta carbons and the metallocyclopentane. But he noticed that something seemed to be happening, and in particular, it seemed like what was happening was these question marks. The starting material was going away, and 2 lumps were generated in a ratio of 2 to 1. And they're broad, so something fluxional is probably going on. And then the other product is propylene. Very clean reaction, under ethylene. Now he was I've already given away the punchline here. He was very confused by, he tried to do kinetics on this reaction, but he couldn't do it because he kept getting different results. But it would take 6 hours or so, unless the room was dark, or the antechamber of the dry box was dark. That's where he put his samples. Then nothing happened. So light is required. Even fluorescent light, room light. Maybe now with LEDs and so forth, it might be a little different, depends on the frequency, but normal fluorescent light has a pretty broad spectrum. And room light was sufficient. These compounds are stable at 90 degrees for days. So what are these lumps? We know what the minor ones are. Minor doublets are what you started with, but what are the 2 other ones? Well, if you cool it down, the sample, the other 2 are the metallocyclobutane, square pyramidal. And if you look more carefully, you can see, if you blow it up, you can see about 1% of another kind of metallocyclobutane, same unsubstituted ring, but it's a TBP with that structure, alkoxide or siloxide trans to the amido group. And that has the alpha carbon at an unusually large shift for reasons that we think we now understand, at about 100 parts per million. And the beta carbon at about -5 parts per million. These alpha carbons, as I showed in this schematic of how this reaction works, are those bond lengths are very short. They're of the order of 2.05 angstroms. A normal metal carbon single bond, which is what it should be, is about 2.25 angstroms. Now, it doesn't sound like much, but in this sort of chemistry, it's a lot. And in fact, 2.05 is a typical metal carbon double bond length in many compounds. So the alpha carbons have double bond character already. That's another reason why this metathesis reaction works. But it only works in TBPs. Well, the TBP is a square pyramid. The majority of it's a square pyramid. There's nothing unusual about it. The metal carbon bonds are much longer, 2.17. So 1/10 of an angstrom. You think that's not a big deal, but it is a big deal because this is not active for metathesis. It has to convert to a TBP. So if you get some LEDs for a few dollars and you make a little reactor, we use 450 nanometer LED lights. We now use, I think we use 405 and 380. We got a fancy little box with some fancy LED coaxial cables. We can stick them in NMR tubes and do very nice reactions. Sunlight works, but LEDs work very rapidly. So with an LED reactor of about 90 milliwatts, the reaction's over in 15, 20 minutes. So it's about 50 times faster than room light, which is pretty weak if it's just a normal fluorescent light. The only products are the Metallacyclopentane, unsubstituted, and propylene, made by loss of propylene from an intermediate methyl metallocyclobutane ring. The reaction is first order in tungsten. It's a photochemical reaction. There's nothing very surprising about that. We think there's no isotope effect. We haven't actually measured that yet. There shouldn't be if it's an excitation followed by a reaction that's not rate limiting. If you change the temperature, you find that it's characteristic of a photochemical reaction. There's really the transition state theory, delta H double dagger, as it's called, is very low, 2 kcals, which is almost nothing. And delta S, the entropy factor, is almost 0. So that's typical of a photochemical reaction. If you run the spectrum of these metallocyclopentanes, you find out that there's a big allowed transition on the left down below 320, going up through the roof, and then a very weak bump there between 320 and 420 nanometers, and then it goes all the way out to almost 520 nanometers. The blue is the emission from a 450 nanometer LED. And so they overlap right at the bottom there to a significant degree, depends what you count significant. There is some overlap, and maybe that little bump is, in fact, the transition responsible for this magical reaction. It's a forbidden transition. The epsilon's about 3,000, which is typical of a forbidden reaction. You can do some DFT calculations. I don't do them myself. A guy named René Riedel did them, learned how to do DFT, and I think he first used a sort of trimmed down molecule, but now he does the full structure. And he found in every case that we've examined so far, the predicted absorption envelope for a transition from the HOMO, which happens to be the combination containing both carbons and the metal in the middle, 2 electrons in that HOMO, taking one of those electrons out and putting into the DXY, which is empty, and gives then 1 electron left in that HOMO and 1 electron in the DXY, and that doesn't sound like a stable situation. And then all hell breaks loose. I'll show you what happens. But right there around 380 is where this predicted transition should be for the 0 vibrational state. And the little bump on the left is, I think, 5 of the next vibrational states, 4, 1, 2, 3, 4, 5, at higher energies, weaker. So it matches. So what's the mechanism? Well, it has to be that, well, we think it's that transition. Has to be, you should be careful when you use words like has to be. Once you make that intermediate excited state, a beta H from the left compound moves to the alpha carbon. That, in radical chemistry, for example, is not an allowed sort of thing. There's only one electron in that HOMO in the excited state and one electron in the DXY. We could say that the H moves to the metal. But we don't think so. We think this is actually radical chemistry, but it's not free radical chemistry. So the H in the beta position migrates to the alpha carbon, which then makes a metal carbon bond and the methyl substituted metallocyclobutane, square pyramidal. That, you'll see, can be observed, but that can't lose olefin. It goes to the TBP, which then can lose propylene down at the bottom left and make the methylene, which takes up ethylene and makes the TBP unsubstituted metallocycle, which collapses then to the SP, favored metallocyclobutane. You can go the other way if you want. I won't talk about it involving a beta methyl metallocyclobutane, but basically that's it. So I wrote observed up there. Is that why? When is that observed? The SP has to rearrange to the TBP in order to lose propylene. As the groups around the metal get bigger, imagine 5 big balls. What are you going to get when you put 5 big balls around a central ball? You're going to get equivalent angles everywhere. It's going to be approximately a square pyramidal. So as the groups get bigger, that becomes preferred, and then rearrangement to a TBP slows down. And that happens when you change the amido group to tritionyl-amido, triphenyl methyl amido, instead of 2,6-isopropyl phenyl amido. That's not triphenyl, it's triphenyl methyl, trityl, on a nitrogen. So it's not even an aryl. It's a special type of alkyl beta carbon, but still different. So when you photolyze that, you get the same thing. You get the square pyramidal under ethylene, metallocyclobutane. The rate at which that beginning material disappears is about half the rate as it does in the disopropyl phenyl amido case. But then the final product overall is 1/20th. The reason is that you can see this intermediate come and go away. And that's the alpha methyl metallocyclobutane, this guy, which slowly rearranges to the TBP, which is why the reaction doesn't go so well. So for the first time now, we connect the proposal that tungsten cyclopentane ring contraction is real, and it's active for making real catalysts of molybdenum and tungsten. So it really connects the two. And that was the first time in all my time or anybody else's time studying this type of reaction that connection's been made. The bottom thing I said, you got to be suspicious of what's in the literature these days if you're working. Now, some people always work in the dark, but figuratively, but usually people have the lights on. So if they're fluorescent lights, then how do you know the reaction is not, in fact, going on? Not only can you make alkylidines via metallocyclopentanes, but if alkylidines decompose to metallocyclopentanes, which we know they do under some circumstances, then you're going to regenerate the catalysts. So that, we think, is happening in the presence of light. But we think probably there are going to be thermal versions of that, especially for molybdenum, which we have to prove. In the meantime, does it work for substituted metallocycles, like the ones shown in this tantalum chemistry? So we decided to make some from propylene, simplest terminal olefin. And you would expect the one on the right to be the most stable one, trans. There are 3 isomers of that. There are 4 isomers of the alpha beta prime disubstituted in theory, never been observed, and the alpha alpha prime disubstituted, 3 isomers of that one. So the one on the right is the most likely to form, lowest energy. So if you take the unsubstituted metallocyclopentane and you put propylene on it and you heat strongly, which Christophe Couperin would say not a good idea because you get a CH activation and you'll make alkylanes that way. No, you don't. You just exchange ethylene for propylene once to get the middle one, 2 isomers, which you can see, and then again to get the final product, the beta-beta prime trans disubstituted metallocyclobutane. In the dark, that's stable at 90 degrees. The crystal structure is exactly the same as the unsubstituted one. Doesn't look like a square pyramid from some angles, but it's square pyramidal with the trans methyl groups on the metallocyclopentane ring. When you photolyze it, guess what? You don't get ring contraction, or do you? The primary product is alpha abstraction. So the primary product, about 90-some%, you take a proton from one of the carbon CH2 groups and move it, or H, let's call it an H, and move it to the other carbon. That leaves an alkylidene that looks like what you see on the right. There was a mystery product, an unknown byproduct. He said, I don't know what this is. And I told him once, and then he seemed to ignore me. So later, after he stewed about it for a while, I found out that it really is the product of contraction. Because you contract, and you make this trimethyl metallocyclobutane, not observable, but you lose propylene from that in the back, and you make a dimethylcarbene. You can make that. In fact, if you add isobutene to the top right species, you make this thing at the bottom. So in this case, it's about 80% at room temperature abstraction, not contraction, and about 20% contraction. Well, you can make a lot of bicyclic species. Now, why do you make a bicycle? We did that for tantalum for various reasons. We wanted to make dimers, rings, 6-membered rings, and so forth. And it's easy to do now because you substitute one double bond and the other one comes around, and you can make these bicycles pretty easily. So with 1,6-heptadiene, then you make what I call the 5-5. So the metal carbon-4 ring and then a carbon-5 ring. And it's square pyramidal with the 5-membered ring shown in the cartoon there, not very well. Square pyramidal with the ring pointed down. Ring pointed up would be a different isomer, so the favored one is pointed down. If you use 1,7-octadiene, you do the same thing. This time you make a 6-membered ring, the 5-6, I call it. And then the junction of the two rings is trans. Interconversion of cis and trans is slow. It takes days at 80 degrees. So it's all about the slowness of this olefin exchange reaction. It's not fast. If you photolyze the 5,6, you get 2 isomers of the expected alkylidene from only alpha abstraction. Why is it only alpha abstraction? Because contraction is just too difficult in these bicyclic systems. There's no CH2 group in the beta position. That's what it comes down to. So the protons in these two alkylidenes, H1 up there and to the right, are these two little ones, two little doublets down here at 7.6, the biggest doublet, and then 8.1 or so. Mixture of about 90 to 10. In another system, we showed that this happens for other alkoxides and other amido groups besides diisopropyl phenylamido and tritylamido. It happens for phenyl itself, phenylamido. Trifluorotebutoxide, this is the crystal structure then of that photolysed dimethyl metallocyclobutane, metallocyclopentane, bicyclic metallocyclopentane, with the 6-membered ring trans, and then a metal carbon double bond. That's the trans alkylidene product. And we have several crystal structures of that type. Everybody would say, okay, but what about supported catalysts? And I collaborate with Christoph Koppere, who's at the ETH in Zurich, have for a number of years now, almost 20 years, more than 20 years, about 20 years. And he studies surface organometallic chemistry, SOMC. So he takes a compound like the one you see on the left, which we provided to a former student, a postdoc of his named Matt Conley, who's my colleague now at UCR, totally labeled, C13 labeled, because we're going to do solid state chemistry on a supported catalyst. How is it supported? Well, then you have to label it, otherwise it's really impossible presently. It's supported on silica 2, SiO2, 700, which means it's been heated to 700 degrees and contains fairly isolated hydroxyl groups. And those hydroxyl groups will protonate off one of the side oxides. So then you get a catalyst that you can show, as I'll show you in a minute. You get a Metallacyclopentane. That is what you see in the middle, number 2, and all the rest is a silica surface. So we collaborated with Matt and Len Mueller, who's the head of department and also an expert in solid state NMR, to do dipole-assistant rotational resonance. So the asterisks at the top are the Metallacyclopentanes supported on silica, shown on the right. And the alpha carbons come where you expect, at 70-something, and the beta carbons at about 30. But there's a whole lot of other stuff there. These are not sharp signals. This is solid state and mixtures of sort of conformations and so forth. And if you heat that, so that doesn't survive. Some of it survives. But if you heat that, those two asterisks, those peaks, go away and turn into all the other stuff. All the other stuff, when you just thermalize, is 2 replaced by 5 and 3. Alpha methyl, one of the isomers, and beta methyl, one of the isomers. If you photolyze, a lot of other things happen, and you also form 3', which is another isomer of the beta methyl. So I am told that these data are good data because this is a difficult technique. But what we've learned is that this is a possible way of, from the very beginning you probably saw this. If you start out with ethylene, you're feeding it in there and you get propylene and a Metallacyclobutane, and if that Metallacyclobutane rearranges to propylene somehow, that's still a big unanswered question, you get propylene. So you should be able to take 3 equivalents of ethylene and turn it into propylene. That's the biggest metathesis reaction out there. I've forgotten the numbers. They're very big. That's how a significant amount of propylene is made these days, which is more in demand than ethylene, from ethylene, which is a lot cheaper. And, but it's using an old tungsten oxide on silica catalyst. We can do better than that, I think. This is the mechanism, Metallacyclopentane, ring contracts, make a methylene, makes a Metallacyclobutane, that rearranges, make more propylene, around and around, round you go. That sample I just showed at 85 degrees does 11 turnovers of ethylene to propylene without making any butene of any type. So that's pretty puny, but nobody's ever shown that before because it's thought by people who use these catalysts, these old catalysts, that it involves a dimerization of ethylene to butene and then a metathesis of butene, 1 butene or 2 butene to give propylene with ethylene. But this has no propylene, no butene formed. So we published that back in 2022. There's much to be done. One of them is to test out the third possibility that Christoph Koppere proposed. That is, something like a propylene complex will rearrange to a Metallacyclobutane. You can show that that's exactly the wrong way. If you take the Metallacyclobutane I've been talking about, and you add a Lewis acid, 5% down to 1%, let's say perfluorotriphenyl boron, or BCF as my students call it, immediately you get the propylene complex. So that catalyzes the rearrangement of the metallocyclobutane to the propylene complex via, presumably, well, number one, it shows that the propylene complex is lower in energy by at least 2 kcals compared to the metallocyclobutane, and number two, that the intermediate is probably a cationic pi-allele complex. And you take off an H from the central carbon, you get a cationic pi-allele, you put the H back on an alpha carbon, you get propylene. Actually, an olefin, in the way it binds to a metal, I mentioned it, donation by back donation, and an alkylidine, donation by back donation, and an allele and a cation, same thing, donation by back donation. Those are the two major molecular orbitals involved in binding. So it's no surprise that you can make a cationic allele. We have much to study here, but it's an interesting finding. And we still have much to learn. I'm not going to talk about it, but another question is, what about molybdenum? Molybdenum will do the same thing. Much more difficult. Number one, because the reactions that I've talked about are thermal for molybdenum. They can be accelerated by light, but also you make metathesis catalysts more readily containing molybdenum. So we still have a lot to learn. This square is what we've been dealing with in the last couple of years. It's really been what I've been dealing with most of my life, but only focused on it in the last couple of years. So with that, I want to thank Maxime is pasted in on the left there. Maxime Beaujolais, he went off to learn electrochemistry. We'll see if that does him any good. He's still interested in organometallic chemistry. No offense to electrochemists out there, but I think he's interested in organometallic chemistry. And I mentioned the other people, and Matt and Len. Veronique is our X-ray crystallographer, who we keep very busy. And UCR made this all possible. So I will stop with that. I'm only a few minutes behind. Thank you very much.
All right, with that, we'll open it up for Q&A. Anybody in the room have any questions?
The host always have to ask the first one. Klaus, I knew that. He was going to come here. Okay. This is a very good organometallic chemist. One of my postdocs, former postdocs.
I remember it well. So, first of all, a bunch of beautiful molecules. I certainly got my dose of organometallic molecules today. Beautiful chemistry. Let me ask you a question. So you're saying the metallocyclopentane does this light-induced ring contraction. But it seems to me that, that and the metallocyclobutane aren't that different. And so can it undergo a further ring contraction, which essentially would make an olefin complex, which blows out and then...
Yeah. So we're starting to think about that. Well, how do metallocyclobutanes rearrange to olefins, which I've observed several times, usually the unsubstituted one rearranged in propylene. I just say, well, it's obviously a beta hydride elimination, allele, da-da-da. That's what happens. We're starting to think that maybe that's not true. Maybe light is even involved in that reaction. But it's also true that we know very little about that reaction, surprisingly. I don't believe an H, this is organometallic talk now, so I don't believe an H ends up on the metal. I mean, this is a high oxidation state, monohydride would be of tungsten. You don't have to name one now, but if you can think of one, let me know, because they don't exist as far as I know. And so the metal doesn't get enough from an H. I mean, it's only one electron, unlike carbon, loves carbon, especially metal carbon double bonds or triple bonds, but not an H. So I don't think H's on the metal are on. The H might migrate to another alpha nitrogen or oxygen, but I just think the simplest thing is in the photochemical reaction, it's excitation and then H dots do what they do to make whatever they want to make. The thermal reaction, if you do calculations on all of these, you get the same big bump, little bump for the 0-0 transition and the upper, higher energy transitions, vibrational states, for all of them, and they're all at 380. The thermal reaction, which would require, if it were the same transition, that transition at 1,000 nanometers. My photochemical friends say, forget about it. I think the thermal reaction that gives an alkylidene is related to the photochemical one, but it's not the same. I don't know how. It may not be a square pyramid. It may be a trigonal bipyramid, or something in between the two. I mean, we don't really know. But you're right. There's a lot. If you start to ask embarrassing questions, there's a lot that we don't know about these Metallacyclopentanes. We know in the TBP form, they lose olefin. In the square pyramidal form, they do not. Is that when they rearrange? We don't know that. Sorry. But I just got renewed, so I'm 5 more years.
So for like a lay person or someone...
A chemical engineer, you mean?
I'm going to ask a question now. But for someone outside of your sort of expertise, why the focus on molybdenum and tungsten? And I know, I mean, there's some industrial reactions that both of those metals are very important for, but it seems to me a lot of the work that you've done over your career has been focused on molybdenum, tungsten, and the like. So, I mean, just share with us why.
Number one, I invented, I think, metal-carbon double bonds and high oxidation states. We know those are the intermediates, those are the catalysts for the metathesis reaction of olefins. We know that only, basically, for ordinary olefins, only molybdenum and tungsten work. Chromium does not work. Vanadium does not work. Everybody wants it to work for iron. Well, come on, you can't turn iron into molybdenum just by looking at it, you know. It's a very, very special reaction. It's not like hydrogenation, right? Take any metal and an olefin and hydrogen and boom, you can hydrogenate it under some conditions. Only, as far as I know, molybdenum and tungsten and rhenium. It's probably rhenium-7, which is much more reducible than molybdenum-6 and tungsten-6. That's probably the active species, rhenium-7, oxidation state, alkylidene. And we've made some, and they do metathesis, but it's more complicated. And rhenium is also very expensive, so nobody's going to use rhenium. Why beat your head against the wall? So the bottom line is only molybdenum and tungsten do this fantastic reaction that has applications in organic chemistry, in polymer chemistry, in pharmaceutical chemistry, in pheromone chemistry, in biology now. You can make mucin mimetic polymers if you choose the right catalyst. So it's still something interesting to study. That's basically it. And UCR supports a couple of postdocs to let me do that and close my chapter on metathesis. I hope I can do it.
Other questions?
Somebody must have another question.
I'm not an expert in what is chemistry, but I wonder more from the application perspective. From an application perspective, you mentioned a few fields and also beginning, you said how important is...
This is applied chemistry after all. Right?
Exactly. So what makes you most proud and what excites you most in future developments that this research can lead to? In
terms of the applications, what makes me most proud?
Yes. can the
Well, I think the effect on organic chemistry, the Nobel Prize was for contributions to organic chemistry. Organometallic is not in that phrase. So they feel that I've contributed a very large amount to organic chemistry because this is a reaction that's orthogonal to traditional organic chemistry. You just can't chop up an olefin and make a new one any other way. You can do it, takes 3, 4, 5 steps and da-da-da-da-da. And it's not catalytic anyway, you know. This is a catalytic way to make olefins from olefins. And it only works for molybdenum and tungsten, basically. So you can apply it in all sorts of ways. There are commercial products now, pheromones made by coupling two terminal olefins, evolving ethylene, and the reverse, ethenolysis of oleic acid esters to give alkyl 9-decenoates and decene, both of which can go into various other places in the chemical industry stream. So it's just a unique way to make olefins from olefins, and it's not over yet, and we'll see where it goes. But you know, I'm not going to be around forever, so better happen quickly.
I've got a quick.
Okay, everyone.
Go ahead.
Yeah.
I was wondering, so in the most of the complexes you had the amido group on there, and you talked about the phenoxy or the phenoxide and how you needed those bulkier groups. I was wondering, since some of the amido ligands had like ortho groups on them, do you think that's doing like a similar thing? Like, is that? I just was wondering, like, what do you think that amido?
Yeah, I thought you were going to ask, what about oxo? Because an oxo is not an amido group, it doesn't have any substituents and so on. Well, oxoalcoholdings are more difficult to make because they decompose bimolecularly more readily. But we already know that you can make oxo Metallacyclopentanes, and they will photolyze and contract, same way that the amido groups do. So it looks like that other double bonded group to nitrogen or oxygen, amido or oxo, really doesn't affect at least the photochemistry. We don't know about other chemistry, the thermal chemistry. And the thermal chemistry is what we're going to focus on next. But there's plenty of photochemical studies to be done, a lot of photophysical studies, you know, finding out what this intermediate actually is, because the photochemistry of organometallics is incredibly primitive even today. Because people just say, oh yeah, shine light on it and it works better or whatever. They don't really have any explanation aside maybe from metal-carbon bond cleavage, which is one way to understand this photochemical reaction, I must say. But the first system that we explored was a cyclopentadienyl tantalum dichloride Metallacyclopentane, as I showed you. And we also explored the alkylidine variant from which gave that Metallacyclopentane. And we showed that there is what I call a dark reaction that's well behaved in making the alkylidine from two alkyls. When you shine light on it, there's also a photochemical accelerated reaction. So there are reactions, I think, related to what I talked about that are both photochemical and thermal. And I think that's what we're experiencing in molybdenum and finding it causes a lot of problems. So we're going to have to figure out how to work those out, if we can. So sorry about rambling on, but yeah.
All right, with that, let's thank Dr. Schrock.
To you, sir.
I was going to go get my pointer, but I see you have something in your hand there.
So we just, I don't know, if you can probably all hear me, right? Yes. On behalf of both the University of Delaware and Comores, we want to thank you for being our inaugural Power of Applied Chemistry lecture series speaker. An outstanding talk describing some of the work that you've done during your career and its applications for those of us who are chemical engineers, the applications of that work. So we have a small token of our appreciation, and I know we'll want to get a...
I know this is my signature because I signed it.
Yeah, yeah. So we'll want to get a quick, yeah, we should.
Oh,
Yeah. So
okay. Thank you very much. I like the yellow ribbon. Nice.
And you might want to...
Okay,
Good.
good.
So, thank you so much.
Thank you. My wife will like that because she is as I said, a fighting blue hen.
Great. So we have reception. Just do
Yeah.
real quick, thank you.
So can I get the members of the organizing committee that are in the room to stand up? I know I've seen at least a couple of you. Shang, Ben. We also had Palin on the Camorra side. We had Professors Johnston and Martin. On the UD side. So really, thank you. We would also like to thank Ann and Christy for making everything happen. So thank you. And with that, we have the reception outside, so please join us. And, again, a big part of this lecture series is getting Camorra's UD interactions, and we'll build more collaborations. All right. Thanks, everybody.
Thank you.